If you want, I can give them some information related to water
Oh, yes.
and the toilets or bathrooms.
Yeah.
So, you remember yesterday classroom? There we have the water and also we have for the breaks, we're going to gather there. So we have the coffee and cookies. Okay, and regarding to toilets, we do have one just going getting out of the classroom. You can go either way, right or left. And if you go right, turn on the right. And before the stairs, you will find the men's toilet. But if you go left, you go till the end, and also next to the stairs, you will find the ladies' toilet. Okay, and if everything is busy, you can go downstairs in both sides, and you have toilets. I'm not sure that one, but that yes. And if even that is closed, you can instead of turning left, turn right, and at the very end you will find the last toilet. But that's only for me. Yeah, thank you.
All right. All right. Well, remote sensing fundamentals. This is a full class, a full semester. So to see, to get an assessment, how many of you have worked or understand the fundamentals of remote sensing? 2, 3, 4. Okay, very good. On the rest, have you interacted with maps of any type, like image from a satellite, an image from an airplane? Yes. Digital elevation models. Yes, I think pretty much everybody has dealt with that or has interacted with that, and it's good. Okay, so what I'm going to explain you is the theory behind any image, either from drones, on satellites on here. Feel free to ask questions if the concept is not clear. And remember, this is a very condensed summary of a semester, okay? So feel free to ask questions. Okay. Okay, how many of you have a cell phone right now? How many of you have Wi-Fi right now? Okay. You got Wi-Fi?
Yes.
Okay. Try to read the QR code. I'm going to show you the. Have you seen this app before? Oh, you're going to love it. Okay. Okay, you get.
I don't have a QR code either. I don't have the application.
Ah,
Just with camera,
yes.
Yeah, just the camera.
and then
Just open the camera and point it to the QR code. It will show you a link.
You can zoom in also.
Yes, download the app. Download the app on your cell phone. Let's see if it can do quickly. But this is one of the tools that you will take with you. It's a really nice app. It's not mine, but I love it. Okay, it's called the One Soil app. If you're having issues, we can try to install it later, but I'll show you how it works. Okay, and there is the guest access, and you can create a login to the app, and it gives you more access to the data. Okay. I use the app. It also have a website, the app, and I went to the New Delta. What do you think I'm seeing there in the image? This is a satellite image for a specific area. It's called El Bejeira Governorate. It's a governorate street and the Guatanella gas station. Pivots, center pivots. Okay. What the colors mean?
They get agricultural land and desert land.
Okay, yeah. But there are levels of green. I have green, yellow, orange. What do they mean? How I can interpret that map? I'll show you how. All right. So the app, what it's doing is using satellite data and is providing information that is called NDVI, Normalized Difference Vegetation Index, for everywhere in the planet. So they figured out how to make it free. I don't know how they're paying for their servers and the app, but they are offering this app for free. They offer other products too for harvesting, for monitoring, planting of crops, but this one allows us to see the condition, the health of any farm in the planet at any time. So we can play with the app during the lunchtime, for example, and we can navigate all over the world. Okay. What is remote sensing? Well, remote sensing is the process of detecting and capturing physical characteristics of objects or surfaces without physically interacting with that object. For example, I can know the properties of that wall just by looking at it. I don't have to touch it to know that that wall is white, that is not smooth, that is arranged in a series of cinder blocks. Why? Because I have eyes and you have eyes that are capturing the reflection of the provided light from the wall to your eyes. And somehow that reflection is telling you that that surface is white, but it's telling me that this surface is black. And it's telling me that my backpack is blue. Why? Why the reflection of that back is blue, the wall is white, and the computers are black? What's happening? The light is the same for everything. So why will everything has a different color?
Because
Go ahead.
because it reflects only the color that we see and absorb all other light, all other
Yeah,
colors
all right.
with the wavelength.
There you go. Where is that absorption? Okay. Absorb. Okay, it's a keyword. All right. So let's go into more detail about that. Now, from that basic concept of reflection and absorption, remote sensing has evolved a lot. We're talking about mapping the extent of flooding. We're talking about evapotranspiration, ET estimates for the entire planet. We can monitor changes and morphology changes on rivers. Here in Utah, we're suffering a 20 plus year drought, and that has affected our major lake, the Great Salt Lake. And we can see with remote sensing the evolution of how the lake has been shrinking until I reach a point where the lake bed is now releasing particles that might affect the health of the community living around the lake. Wildfires. Here, wildfires now, every day's news. Just a week ago, we got a smoke here in Utah from Canada, right? So
Maybe a couple of weeks ago.
yeah, a couple of weeks ago, imagine Canada is having these massive fires that were able to reach Logan. So our sky was smoggy, less intense, of course, than in Canada, but yes, remote sensing. And we can track changes in land surface. We can track changes of if a piece of land was a natural land, then was developed for agriculture or for urban areas or other purposes, and we can see that evolution over time. So this is what remote sensing is giving us and more. This is just a small sample of what this information can give us. The same can be said for drones. And as drones become more cheaper, more accessible, people are finding creative ways to use it. One of the uses is mining. To know how much volume of earth have been moved, we can create a 3D map, a digital surface model with information coming from a drone. We can use it to see variability inside a plot, or let's say we're cultivating corn, and we can see which areas are performing less than desirable than others, that can pinpoint towards diseases, could pinpoint to nutrient deficiency, or changes in evapotranspiration. In environmental applications, we see a lot of documentation surveying. Let's say there is a fire now. These dead trees are creating these carbon sediments that will end up in a reservoir. We can map the extent of the fire, and we can map the extent of this carbon residual that we can see whether that after a rainfall event might end up in the reservoir, the lake, the river, or not. Insurance companies here use drones to assess what's the level of damage, for example, by a hurricane or by a flooding, so they can compensate the person accordingly to what the drone is seeing. And even for golfing, or urban areas, the quality of the turf grass is important. The aesthetics of the green grass. Nobody wants to walk over yellow grass. We always like it green. So how we can assess that? Well, remote sensing gives us a really quick view of the characteristics of the area. Okay, questions so far? Okay, now I'm going to talk about resources. There is a ton of free material, and also today, Sergio will be giving you a pen drive with the presentations of today, and we will use it for the afternoon QGIS exercise. But as we organize the presentations during the week, we will ask you for your pen drive so Sergio can put the new material in there. Okay, so books. I use this book to teach. This book is 20 years old and is still valid. Nothing has changed. Our eyes still see the white color, either we're a child or if we're an old person. Okay, so the concepts are the same, the theory is the same. What is changing is the technology itself. So I compiled a list of books for you. These are the links that I have for our university, but you can access those links and see if you can obtain these books back in Egypt, or you can see if a PDF version is available. But we have books for the process of images, applications for drones, remote sensing for ecology, remote sensing of soils, remote sensing of water resources, urban studies, the remote sensing handbook. This is a massive compilation of remote sensing knowledge, how to do time series in remote sensing. So I'm giving you all these links in the presentation so you can look over them later. Okay, that's about books, but also a lot of material is coming up in the shape of mini classes. And I had the wonderful opportunity to develop a mini course on remote sensing in irrigation that is available online. I worked this with Karen Mesa, and we worked for a National Science Foundation project called HydroLearn. And in that HydroLearn, we developed a mini course that will go more in detail than this presentation about the theory of light, the reflectance, the vegetation indexes, the calculations, some practical applications. So here is one, but there is another course in that program called HydroLearn that is remote sensing applications in hydrology. that also takes you more in depth about the fundamentals and how remote sensing is used for example, evaluating a basin characteristics. So more information, this organization, the Delft University has a spatial tools in water resource management. And this last one, this is my favorite. And if I can, I will invite you to visit this website. This is the official NASA educational material on remote sensing. I force all my students to register here because they send every month announcements of workshops, announcements of tutorials, code for people that are interested in remote sensing. Every month I get a new email there, and I'll show you what there is one workshop next week that I'll show you later. Books. We can buy new books, but also, I don't know if you are familiar with this website. It's called the Internet Archive. It has books in it. This is a website that looks to compile the history of Internet. So if somebody in the past put one of these books for free, they keep it a copy. So if you use this link in the search, or you copy in the browser navigation box, you will get a list of remote sensing books that you can choose. Okay, a lot of material. This is, okay, now going back to NASA. I love NASA. I use their satellites, I use their data. I've built a career with the data they produce, and I love what they do. This is the QR of the website, and as you will have a copy of this presentation today, go and subscribe to this website. At the very end of the website says subscribe. When you subscribe, you give your email, and they will send you every month an alert for a new workshop. It could be a workshop in disasters, it could be a workshop in agriculture, it could be a workshop in the United Nations goals for sustainability. They have all sorts of workshops, not only agriculture, it's all over, it's all societal topics. So this is how I keep myself updated on research, new satellites that are being launched and how other people are using it. So here is how I learn what others are doing with remote sense data. And it happens that you get an alert like this. For example, this June 21st is going to be a webinar increasing NASA Earth Science data accessibility with GIS. So they're creating, instead of you downloading the image, storing it in your computer, processing it in your computer, they're building cloud solutions. You don't need to download the data anymore. You just need to connect your GIS, your QGIS, your ArcMap, or your ArcGIS Pro to these servers. They do the calculation for you, and you just download the final result. So things like that, NASA is becoming very strong. So please, on the ARCET website, subscribe. And ArcGIS Pro, does anybody uses ArcGIS Pro? ArcGIS Pro. Okay, there is a book. It's the only book I found. The cost is $3, the book. But it's a book, it's called Remote Sensing with ArcGIS Pro. It's a tutorial, goes from 0 all the way to classification, regression. It's a really nice book. It's in Amazon, you can buy it. And for every chapter in the book, there is a YouTube video that you can use along with the book. And for QGIS, I couldn't find the book. So what I did find is an initial tutorial to start the remote sensing analysis. We will do as an exercise today at the end of the day for those that work with open software. Okay. That is data information will introduce you to, or the books and the tutorials in the ArcGIS Pro book will introduce to the fundamentals of remote sensing. Now, let's say you want to run data for the entire Africa continent or for the entire Middle East area. These computers cannot handle it, okay? None of these computers, okay? So we have a challenge of computational power, storage, right? And building your own code for that. Now, I don't know if you are familiar with Google Earth Engine. Okay, Google Earth Engine, it's not new platform. It has been like 7 years available, that Google has made an effort to collect the satellite data and products from all different research groups in the world and put them together in a virtual environment so you can develop code there. And when you are done, you can download the data or just keep it there for further more analysis. But this is now, there is no GUI, there is no mouse, there is no functions to select. It's pure code. So the amount of tutorials and resources on Google Earth Engine is increasing over time. So that's what I say. If you have the opportunity to, if you don't know coding, you have the opportunity to learn coding, is well worth it. It's well worth it. So give it a try. So Google Earth Engine, material to work on Google Earth Engine. There is a book now. There are 2 books, one in Python, one in JavaScript. And here is a book of examples of people that have been working with remote sensing data in Google Earth Engine. More material for advanced remote sensing. These are Python modules where there is a lot of functionality that simplify. This module has tutorials now, videos and there are examples of code that the video shows how to run the code, and the code is also available for you. And this one shouldn't be here, but yes, this is some resources for you to take with you and explore. Okay.
Okay, can I just make a statement real quick? So
Yes.
one of the things that we've been trying to do through the center is to get you guys to use more the Egyptian knowledge base, EKB. Yeah, so I've not looked at all at what's available in this area, but just to remind, if everybody knows about that, EKB. Yeah. It's basically resources that are free for everybody who has an IP address from Egypt. Yeah, and there's a lot of really good information in there, so we'd love to have you take advantage of that. If there's material, if anybody knows about material from there that's in this topic area, you need to share that with everybody. It's just a database of all kinds of information, books and articles and so on, that are free to everybody.
All right, that's good. Any source of information that you know of it's important. And
We use this EKB to download all the
journals.
journals from all publishers,
that's fantastic.
ebooks, everything. So it's really like a very big library.
Yeah.
Is there anyone familiar with the information in this area that's available? Does anybody know?
Yeah, it's available. Such of them.
I would like to know what's in there and see if some of books or resources can be recommended for that too.
It's hard for us to access it. We have to have a computer in Egypt that we can access through. But if you guys have information you can share with yours, that'd be great.
All right. Now let's go back to the remote sensing science. Okay. This is remote sensing, or the fundamentals of remote sensing, summarized in one chart. The chart looks complicated, right? It has too many arrows, numbers, and such. But the basic explanation is we have a major light source that will be providing light in different wavelengths. Wavelength is a unit of distance smaller than microns, at which the light particles or photons vibrate. So the sun emits light in all wavelengths. We call them red, we call them green and blue, but in remote sensing science, we use those names because those are familiar, but we use numbers to specify which type of photon is coming from the sun and we are capturing in our sensor. So the light is coming from the sun. It's traveling through the vacuum of space until it reaches the top of the atmosphere. That photon, or the photons, let's say, of the green light, will travel through the atmosphere. Some of them will collide with molecules, with dust in the atmosphere, and their direction will change on this collision. Some of them will travel to the surface over our plant, our bare soil, over the turf grass, okay? And some of them will travel back through the atmosphere and again interact with the dust, with the water vapor, with the gases in the atmosphere, and will be pushed away from their return. But some of them will be able to escape the atmosphere and reach the camera sensor in the satellite. That's the fundament. So the light of the sun in a specific wavelength will reach the surface of a specific area, and that reflection will be back. Now, from the 100% that is coming from the sun, it never returns 100%. It's always lower. And there are two reasons for that. The first is that some of this interaction with the atmosphere will push away those photons that were traveling to our specific area. And the other is that the material itself will absorb some of them. That's the reason we see my backpack blue. The light coming from here, if we are able to decompose it with a prism, we will have the rainbow, right? Red, green, blue, and the intermediate colors, yellow, orange, and such. So all those photons from this light source are traveling to my backpack. But this backpack is absorbing all the red and all the green and only reflecting the blue. But it's not reflecting the blue in the same amount. It's not 100% reflected. It's absorbing some of the blue, but reflecting more blue than green and red. That's why, and the color itself doesn't exist. Is our brains trying to make sense of what is this reflection in this wavelength that I'm seeing? Our mind assign the color. So for example, if we have a daltonic person, a person that cannot see red, what do you see that person when we show them a red shirt or a red object? He might see it greenish. It's our brain saying, okay, I don't have the capability in my eyes to detect the wavelength that we call them commonly red. So I'm going to assign to that another color. It might say gray, it might say green, or purplish. So color itself in remote sensing doesn't exist. It only exists these numbers. So to explain that, the sun is a very hot object. The temperature of the sun is about 6,000 kelvins. It's a very hot object. And the hotter the object, the larger the amount of energy or photons it will put out. These lamps are not as hot as the sun, and we can stare at them. But the sun is emitting such quantity of light that is producing photons that are gamma and X-ray, that are ultraviolet, and a small range is what we call it visible. The red, green, blue is just a tiny fraction of the the diversity of photons that the sun emits. There is a large range that photons that we call it infrared, and another large range that are photons that are microwave type. So we give them names to certain values of wavelength, and I'll give you a homework to memorize a table, and I'll ask tomorrow you memorize the table, because that's how you recognize which type of information the drone or the satellite is providing to you. Okay, so but we have between the 400 and 500 nanometers. We call it blue, between 500 and 600 green, from 600 to 700 near infrared. So let's give you a homework now. Okay. From 400 to 500 nanometers, we'll call this blue. From 500, maybe I should write higher. I should close away this. Okay. 400, 500 nanometers. This is the color blue, or what our brain says looks blue. Green. Red. I wonder if the people on the corner can see what I'm writing.
Yeah.
Is it visible?
Yeah.
Okay. By tomorrow, this is memorized. And every day I will ask for this. And whoever cannot answer doesn't get the certificate. Okay? Okay. Ryan heard that. So, and it's going to be random. I will give you a number and you have to tell me what's the name. This is this is part of the fundamentals. We, the remote sensing scientists, have to memorize this table. Why? Because remember, color is just an arbitrary name. We're talking numbers of wavelength. So if we find a sensor that is measuring a wavelength between this range, we say, oh, we're measuring the blue region, and so on. Okay? So this is what any student in the class has to memorize first day of classes. Okay, what is missing in my table? Can anybody tell me?
Before 400. Before 400.
Oh yeah, that's the UV light. Okay. Minor than 400 UV light. What else is missing? Oh, nice question. Yes. Why is missing that? Well, for many years, NASA's satellites didn't have a sensor for this region for decades. It's just in the future, it still doesn't have it. But this is called red edge it happens to be that it's very important in each red edge. It's very important if you're trying to understand the reflectance changes with plant nutrients. This is strongly related to that. And for decades, we didn't have that. So when we had to learn the table, we learned it here and we learned it here, and we never had the data. But now this data is available. And so there has been a massive work on using this type of photons or light capture with pest diseases, nutrient deficiency, and such. Okay. Homework, okay? All right. So what we're missing? What we're missing in that table? Okay. What do you think we're missing? One key parameter. We cannot do properly evapotranspiration without it. We need temperature, right?
Yeah.
Is temperature in my table? Do you see temperature in this table? Because what did happen is this region. Here is your blue, green, red, your red edge, your infrared, but beyond the 10,000 nanometers, no, beyond the 7,000 nanometers, 7,000 to the 14,000 is the region of thermal photons. And this is the temperature of the objects as them. So we remember that infrared sensor that we had on a tripod yesterday. It has a sensor that can capture photons of light related to temperature. That's how in evapotranspiration, we know from the other bands, we know the health, the biomass, the amount of soil versus the amount of vegetation. But this one tells us on this location, the temperature is 350 kelvins. And that is the key to estimate evapotranspiration with remote sensing data. So we need all of this to do these calculations, although some models, EPT models, use a subset of this information to still calculate evapotranspiration. Others use them all. So depending on the model, we use all the data that we have, or we will use less data. Questions?
What about the reflection of wave coming from sun due to wavelengths as the media change due to change in density of
Here, what will happen when, for example, some of the photons get there? Yes, that's a good question. All right, everybody got the table because I'm going to raise it and you will have a chance to copy it. Like my professor, when I was an undergrad, used to write hundreds of equations and then starting erasing the board. And if you weren't fast, because there were no cell phones, you could miss it. You could miss the equation for the exam. So, okay. So, in satellite work, we have levels of data. And this is important because you and I are living in a wonderful time of remote sensing, where a lot of the science and applications that we had, or manipulation of the satellite data we had to do, now is done by NASA. So we have three levels. We have what we call it the raw data. Level 0. When I started to learn remote sensing, I learned it from here, from scratch, where the pixel numbers in the image were a scale from 0 to 255. That was it. The second is what we call it This is level 1. Level 1 is not the raw data, but now this is reflectance data, the reflection of the light calculated here at the sensor. This is TOA, means top of atmosphere. And that data, while we can see now numbers scale from 0 to 1, still have issues. Because remember, where we have these lost photons that were interacting with property or matter and properties of the atmosphere. So our accounting of those photons is incomplete. Now, so we were asked to do a next step, a level 2 surface data, which means we do extra calculations and address the loss of these photons by the atmosphere. This is the highest quality level of temperature and reflectance of any satellite product. It happens that NASA now provides this data everywhere in the planet. In the past, doing from this to this was a workshop or a half a day. And from here to here, it was another half a day. Nowadays, we're here at the very end, but we need to look for it. We need to specifically look for surface products from Landsat. Otherwise, because NASA offers all three. So if you might choose the raw data and the numbers will make no sense, or you might choose top of the atmosphere data and the image will look blurry or bluish. But here is the highest quality of data, and we will play with that today. Okay, so we're here and we are solving with all the advances in research, all the effects of the atmosphere on the incoming sunlight and reflected to the sensor. That's the highest quality level. But again, any correction is a mathematical approach. And over time, it keeps improving. So we'll have versions of it. Okay. Does everybody understand what is a wavelength? Who doesn't understand? You just raise your hand or
Does not.
okay, no, perfect. What is a wavelength? Why we use numbers instead of colors? Because we are very good at capturing specific types of light. So, for example, a wavelength is a description of the vibration. So when a photon is traveling that photon is traveling to land over my plant and then be rebooted. Every, let's say, wavelength is representing a level of vibration. So the vibration of this photon, the distance of vibration is that number. The more vibrate the photon, the more energy it carries. So, for example, we are told not to expose ourselves too much when we go to the beach. Why? And wear sunscreen. Why? Because the UV light, right? The UV light can damage the skin, right? Nobody says the infrared light will damage your skin. They say the UV light, right? Why? Let's go back to our chart. Nobody tells you protect yourself from the infrared light when you are outside. They tell you protect yourself from the UV light because the smaller the wavelength, okay, in this case, the smaller the wavelength, the more energy that particle carries. So the larger the wavelength, less energy it has in it. So we will choose the number or the wavelength. The shorter wavelength is this fluctuation, this vibration of the photon, while longer wavelength means that photon is carrying less energy. So the thermal data carries the lowest energy from all the ones presented in the table. Okay, having said that, then what is reflectance? It's not reflection, or although it's related to it. What is the reflectant concept? The reflectant concept is going to be then a basic relationship between the amount of light that is coming over the amount of light that is reflected. In this case, we're calling it, okay, in this case, we have E over M. Reflectance then is just the ratio between M over the reflection over the light coming from the sun. This symbol, the lambda, means wavelength. So for different wavelengths, the amount of reflection is different. Now, we talk in general terms about absorption and reflection. Let's see how that happens for different wavelengths. So also what I want to mention here that reflection will be mathematically from 0 to 1. We cannot reflect more than the light source, right? So its upper limit will be 1. And if we turn off the lights, there are no reflection. So the minimum value that we can get is 0. So reflection is going to work in that scale. Now, here is what happened. We see the plants green because the plants reflect more green than red and blue. And that is in the visible region. But in the infrared region, plants do reflect more infrared. A lot of infrared, especially when they're healthy. So what is happening for every wavelength, for any total sum of photons coming for the green wavelength or 500, the 500 nanometer, some of it will be reflected, some of it will be absorbed, some of it will be transmitted. Leaves transmit light through. That's why the plants have multiple layers of leaves, because the photon can travel from the first leaf through, go to the second layer, to the third layer. So that's how plants maximize their obtention of solar radiation. So this is going more in depth into remote sensing, but we will stay into this part, into the reflected realm. Do you need a break? Okay, let's take a break.
If I want to
From NDVI, la NDVI is too little. They put in the deal more. You need red, blue on the Yeah. But what are you using? Satellite data or? Okay, so you will have an image of red and another image that is green, another image. Yeah, okay. You have an AR. Okay, so you need to use, for example, you will know for a specific point, the same point in all images. Okay, you want here is core. So you need to in ArcGIS or QGIS, you have to create a table. And this called the classification. So you'll say core is class 1. Good. What is the R? NIR value. So this could be 0.2, 0.3, 0.15.
Normally, we can have some small adjustment.
Then you can say, now I have soybean.
We could bring a fan in.
Now this can be class 2, and I have 0.15, 0.5, and so on.
Yeah.
This is used by a classification algorithm to generate now the map. So that is a classification process.
So what's your background?
Supervised. This is
What do you
supervised.
do? What's your background?
I know that this is this location is corn. I know this location is soybean. So this is supervised classification.
About accuracy of that,
To increase the accuracy, you need many samples, many locations. Like the more, there is no limit.
Okay.
You can get 60 samples and still the accuracy is bad. So what helps is that, for example, you are evaluating agricultural land, but also capture a location that is bare soil. Adding more classes. That goes into here. Okay? So that tells the model that, oh, let's say 0.3, 0.35, 0.4, 0.5. Okay. Now in the image, you will look for these similar values and say, oh, this is bare soil. I should not confuse it with core. So you have to give them more classes to improve the accuracy. Yeah, to reduce the mean errors. Yes.
So I reduce most to account this regression and how to
is the solar radiation, the incoming solar radiation at a specific way.
Standard name also
In the reflection, it's the light reflected by the surface at that specific way.
when we do take the and increases and also
that reflection.
And it's the types
The surface, every like this is black because it's absorbing everything. It's just reflecting a very little. That's why we see it black. And we see this red because it's absorbing blue and green, but reflects only.
some of
Yes.
Okay. But more from a hydrology standpoint.
Red edge.
And another story must be
Oh yeah, red edge.
but
Red.
Yeah, I write.
also
Yeah,
Okay, yeah.
what's about the
We will see why it's planet red
Small
edge.
distance.
I
write it back.
Okay, all right.
No, I heard it said H's, but I found six.
Yes. All right. Right. Let's.
We're glad to have you. Yeah, it's fun. The first group. It's interesting because you guys like don't know all each other, right? Do you know anybody here already before, or is everybody in the group new?
You have my email address? You have my email, Alex? Because I heard you said.
Yeah.
And,
It's difficult here.
Well,
Yep, yeah, so if you get those to me, I'll.
it's kind of fun. It's, I mean, it's fun to.
So you were in a single background, right?
Yeah.
So one shot, Vicky, she got there yesterday, apparently there's a problem. Yeah.
Really?
Yeah, it shouldn't have been, because we did, so I didn't follow up that. We have one more son, or one more mod. Hopefully she's good.
So what was your name?
Yeah, I'm gonna get her.
All right.
So I'm sorry we can't, yeah, there was.
It's rough
There was a
because
mistake in your.
you guys will get to know our names. Take us the whole time to get to know everybody's names.
They also had.
So, okay, so here's the question.
Double up.
So a lot of times, it seems sometimes in Egypt, people have like,
Hopefully, your room is okay.
yeah,
Stay there.
yeah, like two first names on it.
Good.
From my niece, I have two complex.
Okay,
Yeah.
My son,
Okay, well, that's all.
okay. Uh-huh.
and so my son is his total name, but he has 6 complex name. In passport, he write his name, plus.
Okay,
Okay.
so Murat is just part of your first name.
No.
That's your complete first name? Okay,
She's my great, she's the.
yeah.
Everything was great. Yeah.
So
My
I know I
last
get
name
it.
is Abdussalam. It's not a complex, but it's
You had that in the back, that's
Okay.
not the
but
bag.
some people they have complex names. But my friend is Muhammad Isa. Muhammad Isa is a complex name, but for one person.
Okay,
But now the government won't allow to make complex two part names. Just after Salahin, Abdul Rahman is okay. But Muhammad Isa, this is they can name the two person with this name. So no, it's not allowed to write this for one.
oh, interesting.
But
That's just because
he cannot
Record keeping? I mean, why does the government care? Is it just for record keeping?
And I'll,
Like, for
it's okay.
databases or something?
I will.
Why don't they allow that?
Check with.
So
This is.
for government for data processing as they such the typer may use the name for surname, the middle name, and
Okay, so there may be a little confusion in which states.
I'm bringing back.
but the name is just is two-part name, but cannot use only up for one person as Salahin for one person, so that it must be with Abdullah Salahin. That's one name.
Okay.
But it's like in two-part.
We don't know where.
Abdullah.
I hope it comes.
Abdullah.
Yeah.
Okay.
Yeah, they have it down there.
So I have a colleague who's in Arizona. That's the state immediately south of us. It's very, very desert. 45 C.
All right, yeah, sorry about that.
But they, he is from Egypt, and his name is Dia Eldin Shikar. Dia Eldin, I guess. It's like one name, yeah. And I was always calling him Dia, and finally he said, no, Dia Eldin is that's my name.
And it's allowed.
Because that's like it's
not allowed that can be
because that name is one name, even though there's like a space, it's still one name.
yeah.
Okay, thank you. You're welcome. Yes, yeah. I mean, this is the same plane
My battery is running low.
Oh, time to end the workshop.
Oh, no. We haven't been to the juicy part yet. Where is?
Oh, sure.
Just there, then you can keep tripping over.
Yes, that's the idea.
Yeah, yeah.
Okay, let's start calling everybody back. It's an hour already. Need to wrap it up.
Yeah, so were they?
We've got a field for tomorrow at Cash Junction.
Oh, cool.
Have you been to the Cash Junction fields before?
I think, but just on the road, never.
Okay. I've never been there, but I know he was explaining how to get there and I know where Cash Junction is. So,
All right. We'll go there. Okay.
yeah, so you have a field. It'll be in corn.
Mhm.
So actually, it's a good one because it's corn, teff, barley,
Mm,
and maybe alfalfa, and it has four crops on the one pivot.
cool.
So and then the pivot has regular middle elevation
Mhm.
sprinklers because the last tower is Lisa.
Hmm.
And Lisa, that'll be fun because you can't do catch cans on Lisa. They're too low.
Oh, okay.
And when the data just looks. So I think we will still do catch cans
Okay.
on it, but so we can show really what you have to do is catch and time
Okay.
and do the flow rate for each
Yeah,
one.
maybe later we do another coordination and see how we can help you with that. I mean, you need hands and sort of distribute the people.
Yeah.
So
The one thing I need to check, and I should have thought of this earlier, I just didn't. I might see if we have money to buy some like boots or something.
oh, weather boot. Oh,
I
rain
mean, I've
boot.
got a few pairs, but only a few.
I just have one pair at my office at the lab.
Yeah. I've got maybe 4 or 5 pairs.
Yeah, well, we should warn everybody that this can get messy.
Yeah,
Okay.
get money.
Yeah.
I'll talk to Ryan. If it's possible, I might purchase some.
Yeah, we can go to Walmart.
And let me call everybody.
Time to go back. That's great, if you could do that.
So
Oh, sure. I opened it up, sorry. I thought it was.
That's fine.
Thanks.
I got a bunch of gummy bears in here that I'm trying to give to Jeff. He eats really healthily, you know.
You rides bike, I'm going to the lab here. Yeah, so.
So David's gonna come in the morning.
Okay, so
I don't know, that's what I'm saying.
I don't know. Did you ask him about?
I just told some of us, he mentioned.
All right, let's go back to the session. Okay. What is reflectance then? What's the concept behind the term reflectance?
For me,
For everybody. What is the concept behind the term reflectance? Yeah, I'm asking.
What's the first?
What does it mean, the term reflectance?
The reflection divided by light of sun.
Yes, is That's correct. Is the ratio of the reflected light at a specific wavelength over the amount of light that was received from a light source, in this case, the sun, on the same wavelength. So we say that the scale is from 0 to 1, right? 0 when there is no light, and 1 when the reflected light is the same amount. Other times we multiply by 100, and it gives us a scale now from 0 to 100. Okay, now this is the secret. You are here, great. You're not here, sorry. Okay, so let's see. Let's pay attention to the vertical axis and the horizontal axis. You can see that we're not talking about colors anymore. Here we're talking about wavelength numbers. And in the vertical axis, reflectance. So this is the secret behind remote sensing. Yes.
Or maybe you're just getting to this. I was just gonna say, why do we talk about reflectance instead of reflected light? I don't know if you're getting it covered.
Well, that's a good distinction. Reflected light versus reflectance, they're two different values. Because light itself has units of energy. So when we measure the incoming light, we measure that incoming light in units like this one. Watts per square meter. And when we measure reflected light itself, we also talk about watts per square meter. Then this is incident radiation, reflected radiation. But reflectance is the reflected over incoming, and I got watts per square meter on top, watt square meters over the top. They cancel each other. It has no units. It's just a scale from 0 to 1.
It becomes a property of the surface rather than it becomes less dependent on the quantity of light.
Yes.
Incoming.
Yes. So for example, in winter time, we have less solar radiation, right? So if we were to measure the absolute values, we would have less incident light in winter versus summer, right? So if I measure, it will have a different value here and a different value here. But when we do the ratio, we compensate for that variation of light. So we have a standard. So using that reflectance concept, you can see that now we have reflectance values in the vertical axis. And now we have those numbers that you were asked to memorize, but now instead of nanometers, they're in microns.
Right.
So we divided by 1,000. Though that table divided by 1,000 microns. Okay.
Excuse me. I understand you can measure the radiation,
Yes.
but you cannot measure the reflection.
We can.
Or you can define the reflection because it's a dimensionless.
Yeah. So the incoming light, we can measure it.
Uh-huh.
Okay. We have sensors to measure that. The reflected light, we can also measure it with the same device, but instead of pointing up, we point it down. And if we do ratio of those values, we get this reflectance unit that has no units. So we use that to now see the behavior of the reflectance under different wavelengths for a specific surface. So basically, it's learning this curve that will help you to understand how the the changes in reflectance in light are related with a characteristic or property in the soil. For example, the black line is vegetation. Okay, so why we see the plant green? Here is the answer. How much light is reflected in the blue region for the plant?
Sorry, again.
For the black line,
It's the grass.
that is the spectral curve or the spectral reflectance of grass or vegetation. Why we see the plants green? How much light is reflected in the blue region? What's the amount of reflectance in the chart? 5%, about 5 to 6%. What is the amount of light reflected in the red region?
20.
And what about the green region? So in the red, I got about 15. In the blue, I got 5. But in the green, I got 20. That's more light is reflected in the green region. That's why we see the plant green. Our brain sees that. But it's not pure green. It has some of the blue and some of the red. So these curves, remember that yesterday I showed you a device, I call it the spectroradiometer, a tiny black box with a tiny black handle. That sensor, I can put a leaf, I can put soil, I can put water under that sensor, and it will give me this curve. Okay, so for the grass, I have that curve. Look, a healthy plant will reflect very little in blue, more in green, less in red. In the near infrared, look, it's reflecting up to 50% of it. But in the red, green, and blue area, the maximum is about 20. So if we had eyes to see near infrared light, the plants will be shining. Will be like looking at snow, like very bright. Our eyes have adapted to ignore the near infrared light and only see the red, green, and blue. And we see green and we like it. But if we had eyes to see infrared, we will be wearing sunglasses because it will be too bright. So our eyes cannot see infrared. So remember that I put an extra line in the table that you're memorizing, call it red edge, right? The 700 to the 800 nanometers. Why is called red edge? It's called, this is the 700 to 800 because it's an edge. It's a vertical increase of reflection from the red to the near infrared. This slope, the changes on this slope is related with nutrient content in the plant. If that slope gets flatter, that plant has nutrient deficiency. If it's more vertical, that plant has sufficient nutrients. So those are the experiments that are done with this spectral signature. This is plant. Let's see, do we have soil? Which one is soil? Okay. Let me draw it better here. If you understand this chart, the rest of the remote sensing is just opening files, interpreting the data. This is the key. You learn, you memorize this chart, then everything becomes very understandable. So, wavelength, reflectance, 0 to 1, 400 to, in this case, 900. Vegetation is going to be always. That's the shape. You see this shape? That's vegetation. There is no other surface in the planet that has this shape. It's unique to plants. soil, a concave curve. If you see this curve, that's bare soil. It could move up and down. This curve also could move up and down, but the shape is unique. That is what is called the spectral signature. It's a signature that is telling me this is plant, this is bare soil. How do you think the shape of the spectral signature is for water?
Okay. Fix.
All right, let's see. That's water. Water, what happened is it reflects more in the blue, less in the green, much less in the red, and in the near infrared, 0. So it has to die. So now if I want to do classification of an area, I can look for pixels of vegetation. I will know that the near infrared will be high, the blue and the red will be lower. I will have a peak on the green, but it will have always this shape. The soil will have this concave behavior, and the water will have this shape. So there are a spectral curve for asphalt, artificial turf. Our skin, we can get a spectral signature for our human skin. We can get a spectral signature for this wall, for plastic, for anything. And everything has a unique shape, a unique signature. So then how we use this for remote sensing? Well, 500, 600, 700, more like this, 600, 700, 800. So the satellites are going to take advantage of this. They cannot collect all the wavelengths. They can collect only few. So somewhere, I'm going to have a camera pointing to a key locations in this spectral signature, because they allow me to understand what sort of surface is there. So let's see that. (400 nanometers all the way to 13,000 nanometers. This is the thermal region. Every camera, in this case, Landsat, Sentinel, another satellite, MODIS, another satellite, will have a camera specialized capturing a lot of wavelengths or a very narrow wavelength. So they specialize, every satellite in the sky, we specialize in collecting certain regions of this spectral signature. Some MODIS will collect more, Landsat will collect an intermediate, the same with Sentinel. So, because collecting all the wavelengths, it's almost impossible. It's too much data. And the technology isn't there yet. Although they are starting new projects that are looking to capture the complete spectral signature from space on every location on the planet. Okay. Satellites then. How many satellite projects are? Too many. I spent my life studying remote sensing, and I don't know at least half of these names, what they're used for. There are just too many. So we have satellites like Landsat that are used to study the surface of the planet, the dry surface, the continents, the island, okay? And for agriculture, for urban areas, for environment, that's Landsat. We have other satellites like this called GRACE and GRACE-FO, that their primary objective is to study aquifers and changes in the aquifer. We have the Terra and the Aqua satellites that provide pixel data that is 1 kilometer size per pixel. They are designed to study basin, entire basins for entire countries, while Landsat gives us 30-meter resolution to study inside the fields. Now, the ISAT satellite is designed to study glaciers on the poles. It measures several properties of ice, but also measures height. So this is one of the satellites that is also used to provide a digital terrain model of Earth. The SMAP satellite that you see here, that is used to study soil moisture. So you see that we are starting to get a picture of different properties on Earth that can be studied from space. Not all of them are 30-meter resolution. Some of them are 30, others 10 meters, other 1 kilometers, others are 20 kilometers. Nevertheless, the science of that relationship between the specific wavelength and the response of the property to that wavelength is being explored in different ways. Now, this is NASA. You might be familiar with these guys. This is the European Space Agency, and they have their own fleet of satellites. Those are called the Sentinel program. So the Sentinel program study, in this case, it has radar data that is used to measure elevation. Sentinel-2 captures red, green, blue, near-infrared. It doesn't have thermal. That was a mistake of them, but they are fixing that mistake. Sentinel-3 is thermal. Oh, the Sentinel-2 is RGB near-infrared, 10-meter resolution, better than Landsat. Good. But when they launched the Sentinel-3, the thermal is 1 kilometer resolution. So what happened there? But this is going to be improved in the next years. They have Sentinel-4 is to study air pollution, light. Remember that that interaction between the photons and the atmosphere that we explained? That itself became its own satellite, its own study, and that's Sentinel-4. Sentinel-5, again, is air pollution, ozone, solar radiation, and Sentinel-6 is elevation data. So what you want, what data you can get from satellites, it depends which satellite you have access to. Pretty much everything here and everything here is free. Free. But not everybody captures the same data. Now we have Sentinel here, and they capture the blue, green, and red, multiple red edge, near infrared, but Landsat blue, green, red, no red edge, and infrared. Why they do that? I don't have an answer, but it has to deal with technology access, funding, and input from the scientific community. But the one that weighs the most, I think, is money. So, like, they got a budget and they have to prioritize. So Landsat gets RGB near infrared, shortwave 2, and 2 thermal cameras. The older satellite, Landsat satellite called 7, it has only 1 thermal camera. But MODIS has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 thermal cameras. Because in every region, in every wavelength change, there is a different behavior of the spectral current. So this is very specialized satellite. This is a more broad application, satellite, Landsat, and Sentinel. Questions? Okay. Drones.
We had a question back.
Yes.
On a spectrum, it can still. And in clear water, I have a peak that appears in the wavelength, the ratio between 0.5 and 0.6, 1. And its ratio is related to green, not blue. I don't understand it.
Say that again.
And reflectance curve.
Yeah.
In clear water curve, okay, there are peaks that appear between 0.5 and 0.6, and they're related to green. Yeah, not blue. One.
Oh, this is blue.
Yeah. There are a peak.
Oh, the peak.
Yeah.
I am not sure why this is, but basically this curve should be like this. Always coming down. The highest reflectance comes from blue in water. It's like a concave curve, but it ends here. This peak, and that can happen when you have vegetation in water. So if you have a mix, algae and water, you get the peaks.
Hey, you see algae. Okay?
Yes.
But you see here it's clear water.
Yes, it should be. Yeah, this is the guy. I don't know if it's alive. Okay, but this curve should be higher in blue, and it should disappear when we approach near infrared.
Okay, thank you.
Yeah. I'm glad I put the citation.
You put it, clear in parentheses.
Yes. Okay, another question. That was a good question. Yeah. Another question. Clouds. Oh, fascinating. Okay. This is the trick. You go to internet and you ask the spectral response clouds. Go to images. Let me see. Snow also has a spectral response. It's very bright. That's why you are asked to wear sunglasses if you are on a sunny day in a snow hill or a snowberry. But we see it white because the amount of reflection in red, green, blue is almost the same. That's why we see it white. But the star start moving into the near infrared, it starts declining. It goes really close to zero in the near infrared area. It's like black. If we were able to see infrared of snow, it will look like these computers, black. But then you see that waving behavior, and that is related to certain water properties and light interaction. But this is the spectral response of a cloud. Everything has a spectral response. And the changes on that signature, this is related to what we call it the water band absorption. These study in these regions tell us how much water is stored in the cloud, how much water is being carried by that cloud. So scientists use that to do the forecast, to say, okay, there is a high percentage that is going to rain because they see that this value in these spectral regions is low or is higher. So they change that way. That helps. All right. Okay, where were we? Okay. All right. Satellites, we talk about this. Drones. Drones mimic satellite technology. So again, you recognize now this signature, right? Yes. What is it? Black. Yes. Always. If it has low blue, slightly larger green, low red, large infrared, that's plant, always. And you see, a healthy plant will have larger infrared, a plant that is suffering from stress, the near infrared reflectance drops. And this slope start changing. The red edge slope start changing. So we cannot measure all the wavelengths, so we will pick in the sensors of the camera specific regions that each variation can tell us something about the surface we're flying. Okay. How the spectral response changes. We have a green leaf that is turning yellow, that is turning orange, that thing is turning brown. This is a dead leaf. See, the green leaf has a very nice red edge, very vertical. When it goes to yellow, the red infrared, the red reflection increases. Then when it turns, yeah, the red leaf starts changing this way, and when it becomes brown, it changes, now is flat in this region. So these are the changes we track in remote sensing. Changes in the spectral signature of vegetation, soil, water, any forest areas. That information that we get, the reflectance, we use it to estimate or quantify changes. This is a plant, this is a flower, that the solid line was a plant that has plenty of water, nutrients, nothing was missing for that plant. Perfect solar radiation is the thick line. Look how the spectral signature. Now we're not in the near infrared anymore. We're in the shortwave region. So look at the shape. This, you learn lower, higher, lower, red edge, near infrared, but the work continues beyond 1200 nanometers. It behaves like this. These regions are really important because they allow us to study water content in the object. These regions are, if a sensor, let's say a satellite technology captures this region, we can study soil moisture, or we can study water stress in vegetation. So as the plant starts getting less water in the soil and reduce the amount of water in the leaf, the second line is the response to that lack of water, that reduction in water. As we approach towards 5% of water content in the leaf, look, this is the 5% spectral response. So you see that here is changing this way, here is changing this way. In other regions, you barely see the changes until you see the maximum change. So what we do then to study, when we want to study, for example, water content in vegetation, we're going to look where in the entire spectral signature we have the widest variation of reflectance, because that's our target. That variability in that information will tell us something about here. But in locations where all of them overlap, you cannot tell much by the variation of the reflectance. So we ignore these parts and we stay with the locations where we have the maximum variability. Fun? Fun. Yes.
So we measure with the drone, basically have the sensors for the infrared, detecting infrared radiation reflectance and microwave reflectance?
No microwave. Microwave is a part. There are. I've never used and never seen, but I've heard of radar units for drone. But typically they go up. The more available sensors go up to thermal. So we will have the blue, the green, the red, a red edge value, a near infrared, and additionally the thermal. That's as far the drones have gone.
Okay. So we measure the water stress in the thermal radiation.
Yes, and at that point, if we don't have the shortwave range that is between the near infrared and the thermal, then we have to look. If my sensor is measuring up to here, and also measuring this one, well, I have to look which region I get
The most variable.
yes. We will adapt to the data we have. Okay, so we're almost done. We're almost done. Okay, vegetation or canopy, natural or agricultural changes over time. Especially here, we have a snow cover early in the month. Then we have this development of the leaves, the leaf, the flowering, the fruit formation, fruit maturity, and readiness for harvest, right? As the vegetation changes, the reflectant value changes too. And we use satellite data to track the phenological changes of the crop. When we're in bare soil, we will have specific values of reflectance, but as the vegetation develops, our near infrared values will go up. So we could track these values or the changes in vegetation using reflectance, but becomes hard to understand. So what the remote sensing group does, where we do scaled, we're going to do pixel algebra. Okay, which translated is vegetation indices. We're going to develop algebra that combine the red, the green, the near infrared to check how these changes happen. One simple methodology is dividing the near infrared over the red. That was one of the first vegetation indices that were developed. But this is the most used index in the remote sensing community, the normalized different vegetation index. So it's a subtraction between near infrared and red divided by the sum of both. Now, why near infrared and red? What do you think we are subtracting those two? Remember your spectral signature of vegetation. Is the near infrared values smaller than the red reflectance values on vegetation?
The reflectance of near infrared is much larger than the red.
It's always larger.
Yeah.
So this is always positive, right? Divided by the sum of the value. So what we're saying is if the results of this value are closer to 1, that vegetation is healthy. If the values start declining, are going towards 0, either I have problems on the vegetation or the vegetation hasn't covered the entire area. I might have bare soil patches in that pixel area. So we have studied this vegetation index so much that we have a table, another table for you to memorize. And this is if you are getting lunch or not. Okay, so, okay, NDVI. This is, I'm going to give you this one because it's the most studied index in the planet.
Yeah.
Okay, so 0. Okay. NDVI, if the value is close to 0, water. That pixel is water. From 0 to 0.3 is bare soil. This is vegetation. And here is, it might be under stress. Or mix with bare soil. This is how we can take an NDVI map, put those thresholds, and we know if a spot has issues, if I have pure bare soil, or the vegetation is healthy with this table. Because the values that come from the NDVI tend to be from 0 to 1. Sometimes you get a negative value, and that happens on soil. Sometimes it happens, but it's bare soil. So we force it to 0, or we classify those values as bare soil. But this is the table. If I calculate an NDVI of any location, either with drones or with satellite, I look at my numbers and I can tell which areas are healthy, which areas I need to give a second look, because the vegetation, if it's lower than 0.7, might be suffering some water stress, nutrient stress. I don't know, but some level of stress, or it's not fully developed and I still have patches of soil into that pixel. So this requires a second observation. If it's below 0.3 bare soil, there is no discussion. There is no plant. It might be a tiny plant emerging, but not enough to cover the pixel. As such, and how many vegetation indexes are out there? More than 200. Studying them all is very difficult, or it will take a lot of time, but these are the 3 basic vegetation indexes to look at. The ratio of near infrared and red, the NDVI, and the SAVI. The SAVI, what it does, it's similar to the near infrared, but put a correction factor to eliminate the soil effect. So it's, when you look at SAVI, you're just evaluating pure vegetation properties. And this is a clever and simple addition to the equation to do this algebra. And we do this calculation per pixel. That's why it's called pixel algebra.
Yeah.
And we will do this later. All right. This is it. Yes.
I have a question about the normalized difference water index. Can you share it with us?
Water.
Normalized difference water index.
Okay. It's okay. The normalized different water index is not NDVI. Normalized difference water index. There are 2 versions of this index. Okay, one is short wave minus near infrared over short wave plus near infrared. This is if you have short wave data. The other version that I've seen is, let me remember, this with green, is, I think is green minus near infrared over green plus near infrared. There are 2 versions of the same equation. What happened is the 2 papers proposed were published at the same time. So there are, and both of them call it their equation normalized different water index. But yeah, what it does, this index, it allows you to to identify if a location has water or not. So if values are, let's say, positive, they're water. If they are negative, there is bare soil or vegetation or rocks. And so, but if each index like sort of flip the range that is considered water or bare soil. So right now I don't remember which one relate the positive values to water and the negatives to soil, but I know there is a flip in the equation that does on when we use in this equation that for another, the second index, the negative values are water, the positive values are vegetation or bare soil. But it's an index to filter out data. Oh, one way this index, especially this index, has been used in agricultural land is to have a sense of stress, water stress. It's the first approximation to see if stress water conditions are uniform in the farm with the short wave.
If I like to expect towards a flood inundation map, how can I make this?
Well, what as I was saying, you have to check, do the calculation with either of the equations and check if the positive values or the negative values are water, because the other will be bare soil, will be vegetation. So it allows you to do a quick classification of the pixels that are related with water. Yes.
So which one is more accurate? Is all or which one of them is more accurate?
Of these two equations? Oh, these ones. It depends how you use it. This one, this index, the NDVI, is an overall index. It just tells you if the plant is healthy or not. That's it. If it's above 0.7, healthy. Below, it seems not healthy. It's just that. So when we look at forest NDVI or alfalfa NDVI or orchards or trees NDVIs, we are looking at, when we use this index, we are just saying, is it healthy or not healthy? That's it. But Savvy is trying, okay, let's remove the soil effect and let's try to, but if it's health, if it is truly healthy, the vegetation, so try to refine on our interpretation of the NDVI. So if the values are closer to 1 is healthy, if it's is going lower towards 0.5, 0.3, there is an issue with the vegetation itself. So this is focused on vegetation. This one is focused on water surfaces and stress. I've seen indexes that try to calculate or determine if a pixel is absolutely bare soil. There is no vegetation on that. It's called the normalized difference bare vegetation, bare soil index. So there is actually a website. Let me see. Where is this website? I'll find you that later. I don't remember exactly the website right now. Okay. Any other question to close this part of the remote sensing theory?
Yes, I want to ask about the third the indices.
Yes.
No, the one before, I think.
Or this one? Oh, this one of the first vegetation indexes that were developed. This index is very related with biomass. The minimum value is 0, NDVI 0, this value is 0. But this doesn't have an upper limit. It goes from 0 to infinity. So this is harder to manage, but this value relates better with changes in the biomass. So this has been found to be useful when calculating leaf area index. The NDVI has problems to be related to biomass. Because at 0.7, any change in vegetation doesn't change much in the NDVI values, but this one keeps just going larger and larger. So this is a really good index to have, but the problem is there is no way to put threshold like we put for the NDVI, because this go up to infinity.
So we use it to quantify the biomass existence?
We use it to quantify biomass. All right, should we take another 5-minute break? Or how are we on time?
We're at an hour. Not much.
All right, so I still have an hour or some sort of an hour. Okay, let's take a 5-minute break and let's be back for the second presentation.
So 5 minutes US, not 5 minutes yet.
Okay.
It's like 1 minute. Okay. Right? Yeah.
No, la página web donde está hay una página web donde está cada beneficio.
¿De dónde viene esa aplicación?
Su aplicación, está la vegetación, está su referencia y está su uso. Es una página verde.
Sí.
Es, a ver. Ok, tú te encargas de reportar.
Cuando venga les daré, ¿no?
And spectral bands slide.
Yes.
Spectral band slide in existing. That's
Okay.
So you,
Yes.
What's this peaks?
Huh?
Peaks.
Oh, so it means that it's not going, this is going continuously, but here we break.
Yeah.
Because this is 20, no, this is 2,000, this is 10,000. Because between here, there is nothing. There is nothing to measure. It's like, so there are, yeah, so this is the thermal. This is the optical. If we make the scale, this number will up to here, and we will have nothing to show in the middle. So we're just bringing this, the thermal closer to the optical. SAR? Yeah. SAR. I haven't worked much with SAR, but it's becoming more sensible. The data comes in decibels. It's not reflected. Decibels, sound units. Okay, and this is a negative log number. Okay, so but if you do, for example, you plot a star, let's say I have NDVI time, bare soil NDVI going up to 0 to 1, plot a star, I will get the same curve, but negative. But the interesting thing is that they have the same shape as NDVI. So molecular study is to complement NDVI with which cloud. But if we find the equivalence, we can fill it up here.
Yeah, I'm gonna go now, I think, I've got to
We'll make the problem. We'll solve the problem.
She's coming in.
And yellowish.
She's on the plane, I think.
Yellowish.
She'll be on time. So,
It could be a stress or it could be senescence. It's the plant die. So it's mature enough. Not, yeah, it will depend. So like for here in the US, the trees become yellow.
I don't know.
And because the leaves are dying, and that's okay. But yellowish means for yellowing soybean, like
Do you have any?
that means nutrient deficiency. So
So.
by collecting
Yeah, so we just need to make sure that somebody keeps track
signatures
of Dr.
of levels of yellowing,
So that we know, because
okay,
I'm gonna
we
be
can
like those in around three.
find
We won't
a
be back
region
till after.
where that can be used.
Yeah.
Maybe here we see the most spread, maybe
So
here.
we need
So that's the experimental, like you do in a greenhouse, you put a plant with full nutrients, 50%, and you start building with that device, you start
Yeah,
building.
and I'm supposed to be on that, so.
Okay.
So that's,
that should be able to-
Okay, so if you're on that, you know, that's one way.
oh, liver index. Yeah,
Yeah.
from SAR. I haven't read
So
on that.
she'll be at the.
But
hotel
what I know is that the
5:30. So when you guys get back, if you just check.
LAI,
She knows about it.
okay,
Yes, I
That would be.
when you compare it with NDVI,
And I'm gonna look for their facts.
it goes flat. Okay, but then the NDVI
Yes, and I communicated with her and so I, yes. Yep.
around 0.7 doesn't change, but the true
Yeah.
True
I-
LAI.
so I checked on the flight, it's in.
it's increasing.
So
here,
it's in the air, it's on time.
So that's why
That's right.
this one,
It's still coming this way, so I think it's okay.
this is better. It follows the LAI. So this index is better than NDVI to calculate this.
Which model? The difference.
Yeah,
Big difference.
Well, there are two ways. One is with drones. The drones collect picture here. The next picture is here. The next picture is here. So for the same location, it has 3 points. Okay. So if I see, let's say my camera is here, camera is here, my camera is here, and we have a hill. This
Yeah,
camera is
yeah,
looking
so-
here, this camera is looking here, this camera is looking here. This is trigonometry. So if the drone
Okay.
can produce a
And so
3D,
you can dare to
it's
like
pure
fly one.
trigonometry.
I can't fly one. because I don't have one.
No, nothing like that. This is pure. So this
I don't have one
this
yet.
is how we get like
But a lot of.
for trees. Okay? We,
So you
when
have to
the
have.
drone is flying,
drone
we see
makes
the same point for multiple
To
pictures. The
fly.
software does the trigonometry.
So I can try
Yes.
this. You're this.
It's that's not the.
You actually, yeah, it's totally different. Yes.
Also for satellite, this is trigonometry. Also.
They have like that. They measure, they do measure this.
What's
They
important is
measure
that
time.
every
Science.
flight.
They measure the photon going here and going back.
Over, if
So-
there's a problem.
If this distance is longer than this distance, and this distance, so they do some bit of trigonometry too, but
Yeah.
measure time.
Yeah.
And that's what
Both
they
of
do.
the drone, man.
Especially and
So they fly lower.
They, yeah, I mean, drones can find very fine, but this, the satellite does it for the entire planet.
Yeah.
Yes.
Okay. Sorry. What's your name? And which, what university? Okay, so you come from the environmental side.
Yeah.
Okay, so you're kind of falling asleep right now.
Here, first you on the website.
That is a really good question for Alfonso,
So
because he's the one that found all of those. I don't know if they're only available like for our library system. There's- Yeah.
Yeah, by the way, I was.
Uh-huh. Yeah, so that will happen. So he's gonna finish up on some theory. And then we're gonna spend most of the time, yeah, we're doing it all in Q. So that anybody can do it. That was the idea. Yeah. So that was, so they actually went to, they spent most of their time preparing for this, figuring out how to do what they've been doing in ArcGIS in Q, so that it's a little more flexible. And so we'll do some, I think today we'll get as far as doing vegetation index calculations with Q. Tomorrow is gonna be a complete sidestep, and we're gonna go and do an irrigation system evaluation on the center pivot. And then we'll be back with the remote sensing stuff. Well, actually on Monday, we'll be in the field doing canal flow measurement and looking at some surface irrigation fields. And then we'll be back all heavy on the remote sensing after that. Going and moving into the day filled with the drones. And then we're gonna be doing ET modeling with the imagery, and hopefully with the imagery that we collect. So that's the idea.
Okay.
But if it's like a cloudy day or something, they have data that's already available.
All right,
So
let's
to make
go
sure
back.
that we had data for the site. So that's
Yes, and we can talk during lunch. Yes, yeah, but I'll be happy to answer any question. Yes, okay.
Thank you.
Yes, let's begin. All right, welcome back, everybody. Oh, I'm getting a call. Okay. All right. I wanted to mention that how many vegetation indexes are out there? Hundreds. I will say 500 vegetation indexes. Can we study them all? Well, no, but there is a nice website where there are a lot of vegetation indexes already listed. So, for example, this is the most important. If I'm interested in studying water and I want a vegetation index, I'll pass this website to everybody, but it's called the index database. And I go to show indexes for selected application. Here I have a list for crop yield, for irrigation, for precisional, for forestry, for more experimental sensors called hyperspectral remote sensing. I have for soil contamination, different properties of vegetation. If I'm studying chlorophyll or LAI or nitrogen contest or salinity stress, there are indexes that somebody already studied and is listed here. So this is a nice resource to have when you are looking for studying, for example, aquatic vegetation, or you are studying on nutrient deficit on vegetation. This is a good place to start finding indexes that are developed for that task. The website is called the index database. Okay, it's time for us to move to the next topic. And the next topic is not this one. This is for the afternoon. Is ET. So now we know or we have an idea what remote sensing does and how we exploit that data to understand what's happening in the surface. We have to talk about temperature, but temperature is an important parameter, especially for this task. Temperature is the major piece of information for ET. It has proven over time that including temperature in the ET calculations, the values compared to the eddy covariance becomes more robust. So temperature is important, and temperature has a really nice relationship with ET. There was one study from a colleague called Richard Allen that he showed that if you were able to plot ET and you were able to plot temperature, the relationship between ET, actual ET or crop ET, and temperature of that same location, the relationship is like this. Is linear. Is the opposite. Higher temperature, lower ET, colder temperature, higher ET.
Oh, it is.
We're talking surface, land surface.
Yes, this is temperature of the surface of the crop.
Uh-huh.
So low temperature, high temperature means that that location either has a low concentration of vegetation or is bare soil, or the soil is dry. But if it's cold, that location, then it means there is water there. The water is the cooling source of that location. So the plant is transpiring water because it has plenty of water in the soil. So ET is larger. So this is the relationship that our colleague in University of Idaho showed us, and this relationship was linear. Okay, having said that, what do we know about ET? So the goals for this presentation is to summarize the concept of evapotranspiration, identify methods for direct measurement of evapotranspiration, and explain how ET is generated by spatial data. This is a nice diagram that came out a year ago that tries to combine all water processes that happens in a region or a basin. And evapotranspiration is mentioned here because evapotranspiration is going to happen in agricultural land, but also in natural areas and in urban areas too. So evapotranspiration is a concept part of the water cycle. Now, how many different ways we have to explain evapotranspiration? What is evapotranspiration? How do you explain evapotranspiration?
The evaporation of the water from the plant itself, like the leaf area.
Okay, very good. That's one. Very good. Is there another way to explain evapotranspiration? Is there another way to explain evapotranspiration?
Yeah, I think it's some of evaporation and transpiration. It's
Yes.
different process.
Yes, that's the combination. Yes, that's good. Is there another way to explain it? What if I tell you if evapotranspiration is the consequence of another process happening in the plant? That plants are alive, and so they are getting energy from the sun. With that energy, they do this process called photosynthesis, right? Where we absorb CO2 from the air, atmospheric CO2, and convert it into organic CO2. That's how the leaves and the trunk and the flowers are generated. So that process consumes energy, and as a byproduct of that carbon process, the plant transpires. So I can explain evapotranspiration from the cycle of carbon happening in the plant. That's another way to see it. So that is telling us that evapotranspiration and processes in carbon are linked. And this is important because when you study climate change, we talk about a lot about CO2, right? Being of this greenhouse gas, and plants are reacting to that. So they are intaking more CO2, therefore they are transpiring. So climate change is causing evapotranspiration to increase because of the larger amount of CO2 that the plants now can ingest. So there is a link between carbon cycle and the water cycle. The other explanation, another way to see evapotranspiration is from the energy balance per se. We have this solar radiation coming from the sun, okay, some part will be absorbed by the atmosphere, some part will be reflected by the atmosphere. What reaches the surface, what is called the net radiation, is the energy that we will use to warm up the air in the atmosphere, to warm up the soil, and for the plants to use it to transpire. So from the energy balance concept, evapotranspiration is the amount of energy from the net radiation minus the energy that the soil absorbed minus the energy that the atmosphere took that is left over for any vegetation to use for cooling purposes. The plant cools off itself by evapotranspiration, keeps its temperature cold. So that's another way to see. So you are seeing one that is related to carbon, another that is related to energy balance, and the other is by biomass. I could say that the evapotranspiration of a crop is the transpiration process that will change based on the amount of biomass in the farm or at the site. The more biomass, higher ET, lower biomass, lower ET. So I can explain ET not only from the water balance that we're accustomed, but I can link it to carbon, I could link it to energy, I could link it to biomass development. So ET is a concept that is shared among many disciplines, not only irrigation or not only agriculture. So as you understand evapotranspiration, that knowledge can be applied, can be combined with other disciplines to understand better our environment. And this is what we know. Our water balance for our farm, we have the root zone with the water, we have the irrigation, income, rainfall, we might have deep percolation or canopy rise, and we have runoff, and we have the evapotranspiration system. And this is what we're familiar with. We can see that the scientists studying carbon cycle also uses evapotranspiration to describe this linkage between carbon and water in natural, in urban, in agricultural areas. And we go to a basin-wide scale, we see that evaporation and evapotranspiration are part of the entire process. So it's not only us that are interested on knowing ET, it's pretty much everybody too. How we use ET? Well, we use ET in agriculture for calculate irrigation water needs. We account how much ET has happened since the last time we irrigated, and that's the amount of water we have to put back in the soil, right? But there are more uses. Urban areas, we are using it for cooling effects of the vegetation in urban areas, also to evaluate changes in hotspot. Are you familiar with the concept of urban hotspots or urban heat island? Yes. Yes. So when an area doesn't have an urban area doesn't have much vegetation, the solar radiation gets emitted by the concrete, the asphalt, and like walking at midday, is an activity that will make you transpire a lot because you are now surrounded by all this heat emitted by man-made materials. But areas where we have vegetation, the evapotranspiration creates a cooling effect. It reduces that or mitigates the heat coming from all these man-made structures. In agriculture, yes, we're interested in water balance, in irrigation. In forestry, we're interested also in the recovery of the wildfire or water balance, for example, to allocate water from rivers and creeks to keep an area healthy. For aquifers, when we study groundwater, evapotranspiration is a component to do the water balance for the aquifer. How much is extracted or how much water will be extracted by the agricultural sector when managing an aquifer? Well, ET is the number. Drought will have, what's the impact of drought? We can measure it of different ways, like areas that were planted versus not planted. The other way is how much water has been used for agriculture by evapotranspiration means. And carbon, we mentioned that the carbon cycle and the water cycle, when we evaluate vegetation, are very tight. And at basic scale, water balance. What are the factors that affect ET? Well, I found a really nice list, and I agree. There are local, large meteorological and micrometeorological factors, as well as large geographical and local geographical factors like slope versus latitude and altitude, topography, crop factors. The nature of the vegetation itself is going to affect the rate of ET. For example, to give you an idea, when grapes are produced, they are put in rows, and some producers put it every 6 feet, which is times 3, like about 2 meters separation, but others put it every 3 meters separation. If I try to evaluate that area, that spacing change is going to affect the totality of that parcel, of that block. So nature of leaf, nature of stomata, which is a plant physiology concept that I'm not well versed on it, but there are what is called the C3 and the C4 type of stomata. The C3 is the one that I think self-regulate depending on the environmental conditions. And I think C4 is the one that the stomata is always open. Like trees tends to regulate their stomata, but alfalfa is just happy transpiring as much water it can. So the nature of the plant itself will affect it. Soil factors, and I think we have a good knowledge on how texture and structure is going to affect the water retention, and then affect is going to be related with the effort by the plant to use that water, and therefore affect evapotranspiration and how we cultivate. mulching versus not mulching, having a cover crop between lines of rows of trees or vines, the type of irrigation we apply, surface versus drip versus sprinkler, and the drainage system itself, that if there are some high water table issues, everything is going to affect our estimates of ET. So some terminology to clarify all of this. ET, a general name, where when we say ET, we should consider that we're talking in general about the process of water moving from liquid form to vapor form by transpiration or evaporation from the surface. Now, you understand these two concepts, potential and reference ET, which are mathematical expressions of the theoretical maximum transpiration that could happen in a location for a specific type of crop under the current meteorological conditions. So if we talk about ETO, we're talking about this related crop being turf grass, and if we're talking about reference ETR, we're talking about the alfalfa crop. The values are slightly different from each other. Other terminology, ETA or crop ET is the real evapotranspiration for any crop and a given state under the current local meteorological condition. And that's the data that we need to do the water balance. That's the value that we put in our water balance or in the carbon cycle or in other studies we do. Now, how many of you have used the crop coefficient? I did. Okay, the crop coefficient has been one of the major achievements in irrigation science to quantify or to put numbers or to approximate the actuality. And I think my professors and their professors, all of them use crop coefficients, right? And we have memorized the shape of the crop coefficient curve, right? Now, crop coefficient, as we know, is a idealized is estimated from an idealized condition. That means the crop is in a loamy soil with no issues on nutrients, diseases, and is well watered. That's the assumption behind the crop coefficients or the numbers of the crop coefficients. Any deviation from those conditions means that that number, the crop coefficient, must change too. And that's why we have additional coefficients like the crop stress coefficient and the crop management coefficient that tries to make that idealized KC adjusted to the local conditions that are happening. Now, one more term that I need to show you is, what if I'm able to measure actuality? And what if I'm able to measure also reference ET? If I divide those numbers, it will have the same style as crop ET or crop coefficient, but it's not called crop coefficient because this ratio is affected by the microclimate conditions, soil conditions, location where it was measured. So it seems like a crop coefficient, and sometimes we can assume they are the same, but this is, we call it, to differentiate from crop coefficient, we call it ET fraction. Units, well, we have units in millimeters per day, millimeters per hour, inches per hour, but I've seen also kilometers per square meter. I've seen in also evapotranspiration in the energy balance it had to be expressed as energy units. So we will see that studies that do energy balance will express that component, the latent heat flux, that then later is converted into ET units in watts per square meter or energy over a unit of area. So how many potential ET equations are out there? I was told there were about 50, although I haven't seen them all. But if you had a chance to use this software, it's called RefET. This software it can ingest data from a weather station, and you can select which of the listed reference evapotranspiration equations you can apply the data. Really nice to do comparisons if, for example, you have historical data from a certain type of ET, and you have now new data that you can compare how good or how different is the new data versus the previous approaches. Currently, we're using either ETR or ETO in the Pegma-Monty. Now technology has become accessible and have enough instrumentation at weather station that allow us to go directly to Pegma-Monty and avoid, for example, Hargreaves. Hargreaves that uses only temperature of air, extraterrestrial solar radiation, and yes. So, or try to use other groups, for example, have been using, I think, Presley Taylor for decades. So it's a more simpler towards monthly estimates. But nowadays we live in the time where we calculate this parameter hourly. So that's good. This is the Pegma-Monty equation, and you probably have seen it before and studied in detail. But this is the equation that is implemented on weather stations. So we get this parameter already calculated for us. And for the Utah Climate Center, both of them, the ETO and the ETR, are calculated and provided, both of them. If we could zoom in, we can see that there are differences between these two values, and the difference is about 0.2. Is about, yeah, the difference between the, it's an approximation, but it's about 0.2 or almost, yeah, 0.2 ratio difference. Now, for ET, we need to validate not reference ET, we need to validate actual ET. And yesterday we saw the instrumentation that is used to validate actual ET is the eddy covariance tower. So far is the standard that we choose to validate any approach that we might have, like satellite data with, without temperature, a machine learning algorithm if we want to, but we need a ground truth value. And the eddy covariance tower so far has given us the values that we need for validation. And the benefit is that most of the sensors are above ground. Only the soil moisture and the soil heat fluxes go under it, but pretty much all the instrumentation is above, so it's easy to inspect and do maintenance too. Another way to validate or to quantify ET is lysimeters. USU used to have a lysimeter here now, but we don't use it anymore. But in many countries, I remember in my undergrad, we went to visit the lysimeter when we were studying irrigation water balance, and that was the standard for validation of crop water use. So lysimeters can do also the job. Nevertheless, there are certain complications on using lysimeter versus the eddy covariance that makes these more preferable to use. For example, can we put a fruit tree inside a lysimeter? Well, lysimeter have to be very large, right? And probably we will have enough money to build just one lysimeter. But this is replicable. With enough money, we can have 2, 3 eddy covariants along a valley, along a area of study. So we can replicate and do the similar maintenance to all of them. So how we use the lysimeter? Well, the eddy covariance has a footprint, an area from which it receives the the water vapor, the water vapor, the temperature, so the sensors in the eddy are influenced by this area. So we will use this. We will do the analysis with the satellite, the UAV, and we will take the pixels inside that footprint, sum them, and then compare it against the numbers coming from the tower. How we do that? This is how the footprint looks like. So this is part of Harem's urban green areas experiment. The yellow dot is the location of the eddy covariance. The oval shape is the footprint. The data behind it is the UAV information. So for a specific hour, the footprint looks like this. But when you look at different hours in the day, the wind direction will change. So you start having this sort of butterfly shape that we need to use to quantify the daily evapotranspiration. The other sensor that yesterday was presented is the scintillometer, and it's mounted like this on a tripod, and 5 kilometers away is the receptor at the same level. So what is doing this device is sending a laser pulse to the sensor. And so, you know, the laser is it's a compressed light ray, right? So, but as it travels through this location to the receptor, the water vapor coming from the surface start interfering with the photons from the laser photons, making it scintillate. So the intensity or the original intensity of the laser gets affected by the water vapor along the path. So we get a different intensity at the end. That intensity, that change in intensity is related to the sensible heat flux. And with additional sensors like the net radiometer and other meteorological sensors, we can do the calculation of the 4 energy balance components. How the footprint of a scintillometer looks like? It looks like this. The transmitter, the receiver, and this is the footprint on which all the satellite data or the drone data has to be compared to.
If there is a wine in this area, what would like the ET shape in the wine? If there is a wine, wind.
Oh, so this shape is for one type of, or for one is wind velocity. If it increases, the shape will go larger. If it reduces the wind speed, it will become narrow. It's like here. This one has a stronger wind than this one. So the shape of the footprint changes with the wind. So the science on ET has progressed a lot. And part of today is to show you some of the advances that are happening, especially with Landsat ET. There is a project called OpenET, and here is the data. And in the afternoon, you'll get the chance to look at the OpenET dataset. Now is a website now that for any field or region in the west side of the US, you can get historical ET, actual ET, calculated using satellite and different models. Now, NASA also offers a ET product at 1 kilometer resolution using the MODIS satellite. That is called the MODIS 16 product. It's 500 kilometers and is the accumulation of the last 8 days. Also, the US Geological Survey offers a actual ET product called the CBOP model. Is provided at these two websites. In terms of models, let's say I have drone data, I have satellite data, and I would like to quantify or to estimate ET by myself or using my. These are some algorithms that are available. The two-source energy balance model, which is the one that we're going to use in some exercises, it's available for the public. And there are two versions, one that is code and the other version that has already been compiled for QGIS. We're going to use the version for QGIS. The metric model, also in Python version and code version, that can be used for drone and satellite estimation. The CBAL model, that is in a public repository that can be, again, a coding algorithm. And the KC Basel, which uses the NDVI. And there is something very interesting about, remember we talked about NDVI. Why is a widely used vegetation index? It happens that the concept of crop coefficient, the concept like the ratio of actual ET divided by the reference ET, is strongly related with NDVI. In fact, there is an equation for that. If you calculate NDVI and you multiply it by 1.25, what you get is ET fraction. You multiply that by your potential ET, then you get the ET estimation of the. There is another version of that equation that adds a correction coefficient. And I'm leaving you the citation where these equations are coming. But is our pixel algebra by a factor, and we can approximate that crop coefficient. And probably that's the simplest use or the most fundamental use of a vegetation index to approximate crop water use. That is called the KC Basel. See the slide 6. Okay. Methods. Now we talk about the ways to measure true evapotranspiration. We have the eddy covariance tower, we have the scintillometers. We also mentioned the lysimeters, and they are well-managed lysimeters. They can provide that information, the validation data, especially for drones. Now, about crop coefficients, you know this theory. We have a climate, a reference crop, we calculate a reference ET, we apply a factor depending on the phenological stage of the vegetation. We have a crop ET of the crop, but then we know that this is an ideal factor, so we need to adjust it by a stress crop stress coefficient and crop management coefficient, and we get this ETC adjusted to local conditions. And this is well explained in the FAO 56, which when I was a student, this was my Bible. Okay, I enjoy reading this. It is a great demonstration of how clever the previous generations were and how we're able to organize people all over the planet, because the crop coefficients are coming from all countries, the US, Egypt, Peru, Africa, Europe. So there are many locations provided information to build these the paper numbers 56. And that's great. We know the shape, and we play with the number of the days and the number that we put for initial the initial crop coefficient, the development and the senescence, and we play with the dates. We multiply by the reference, and we get our curve of crop ET. But this is what was found when we study either canopy cover or NDVI and compare it to a lysimeter and calculate the crop coefficients. We see this. We see a linear relationship, and this is this methodology, the relationship between the NDVI and the crop coefficient, like having an equation that translates a vegetation index to a crop coefficient, is widely used all across California. The Division of Water Resources and the many research in California use this technique to monitor the crop water use across the farmland over there. And they have progressed a lot into implementing. One of the things they need to do for this methodology, though, the curve is slightly different for every crop. So if we're studying lettuce, the coefficient to move from one value to the other is slightly different than for almonds, than for grapes, than for spinach, than for tomatoes. So they have built this massive record. And when they do this calculation, first they need to know what crop is happening in that location. How the NDVI looks like? Well, it looks like this. It will go from 0 to 1, multiply by that coefficient, then multiply again by the reference ET. We got a spatial map of ET. Now, it is possible to estimate ET from water balance per se. What do you think? If I have inputs about irrigation, I know that I have almost zero deep percolation, the water table is deep enough. Could I recover, and I have soil moisture data, do you think I can back calculate ET? It does, but that's an idealized condition. In many areas, yes, we can assume that the contribution of the water table is minimal or towards zero, but deep percolation assumption that is zero, that's a very serious statement. It tends to be larger than zero most of the time. So, but if we were able to track that and we're able to capture the variability or the changes over a period of time, soil moisture, we can back calculate ET. This is something that one of my students did, taking soil moisture data and the other information in the water balance. This is the red and the green line are eddy covariance data. The bars are the back calculation or the extraction of the ET from the water balance equation. So we were assuming that deep percolation was zero. And that might be wrong because we have some days where our estimation of ET uses spike. And this is because we're making assumptions. So on some days I got relatively good agreement, but there might be days when my technique not work. And efforts or ideas that can track deeper collation are critical. So we can, instead of making an assumption, we can approximate it better. Now, the last approach, energy balance. Why the energy balance has become sort of the favorite to estimate ET is using partial data. One, the technology is accessible. The camera, the red, green, blue, the thermal cameras are already in space or mounted on a drone. Second, the computational capabilities that we have now allow us to process a lot of data faster than before, and we understand better bias issues, necessary corrections to the data to ensure that we are providing to these models quality data. So the energy balance, again, the EDI covariance will measure the 4 components of the energy balance, but these ET models don't. What they do, they will approximate the net radiation, and every model is really good at approximating that net radiation. Then we will make assumptions about the ground heat flux factor. We will say is either a portion of the net radiation, a fixed portion, a variable portion, or a constant value. And then the models will diverge on how they calculated sensible heat flux. Some models, like the two-source energy balance model, its contribution to the science is that it does this job very well. And other models use like manual input to ensure that this H is well calculated. But we don't calculate ET. We assume that if we have net radiation, we subtract these two, all the residual is ET. That's the assumption on when we use satellite data to calculate ET, that ET is the residual of this equation. And we have progressed so much. This is a slide from collaborators of ours in the East Coast in the US. They are working from field level. We're working with them on the UAV level, all the way to planetary scale ET. This is the group, maybe you have heard of Martha Anderson and the Hydrology Remote Sensing Lab from the Department of Agriculture. They are producing this amazing and outstanding information using a combination of multiple satellites. The key factor in all these satellites, they have thermal data. And for us, we learn from them how they do the analysis. We have a collaborator that translated that code to be suitable for drones. And we have been studying over and over time how the model performs for drone data. So how the map of ET looks like with Landsat, like this. The center pivots are well defined. Bare soil is quantified adequately in terms of ET. The darker, the greener, the higher the ET. Brownish colors, very low ET, towards 0. So this is how a Landsat map, Landsat ET map will look like. What are the models that are being used for ET? Well, metric is one of the first models that become very popular, very fast. But metric is the child of the CEBAL model that started in the Netherlands. Then CBOP comes from the Geological Survey National World Census. Our collaborators, Martha Anderson and others, call their model the Alexi bis Alexi, which is what called the two-source energy balance model, and they use multiple satellites, integrate multiple satellites to do. The SIMS is the NDVI crop coefficient method. NASA didn't want to be left out, so they developed a method called the JPL Tresley-Taylor ET model. So all these models are very popular, and you're going to find many papers about these models.
12:50, we should maybe
Okay.
break for lunch,
Yeah, okay.
so we can stick with that part of the schedule.
I am in my last slide.
Better stop now. I'm just kidding.
So how the data, ET data looks with drones. So this is the drone that we saw yesterday. Remember, it was in the room. We've flown it over an almond site that have multiple farms, and we can see the variability of the canopy of the biomass of the tree. It is how the RGB near infrared digital elevation model, the temperature map, plus combination of weather data from a weather station, we can estimate at 3 scale evapotranspiration. So we have progressed a lot in these efforts on estimated, and we can talk more about this after lunch. All right, thank you.
Quick announcement before